Hello, good morning. In this video, I will discuss about the Einstein coefficients and transition probability. So let's see. So the first point comes about the absorption, and as you know that in case of absorption, you required some external energy source to excite the atom, and as a result, the atom goes into the excited state. So the basic process I have already explained, and now the point is about only the transition probability and the Einstein coefficient. What basically the meaning of these concepts. So transition probability P12, as you know, is directly proportional to the energy density of the radiation, right? And so here, what is it means? It means then that when you increase the density of the incident radiation, a large number of the atoms will absorb the energy and as a result go into the excited state. So P12, the transition probability from 1 to 2 state, that is for case of absorption, will be equal to B12U, where U, as I told you, is the energy density of radiation. What is this B12? B12 actually is the Einstein coefficient for the case of absorption, and B12 I can write here Einstein coefficient. Einstein coefficient for the case of absorption, right? And what the information basically these Einstein coefficients contain, right? That I will discuss in the third process. So the main point is about it. So transition probability in case of the absorption is this one. So let us see in case of spontaneous emission. What is that? In spontaneous emission, you know that in spontaneous emission process, excited atoms jumps into the ground state after 10 raised power minus 8 seconds and emits a photon in a random direction. Right, those photons are not in phase, so that's why the output is incoherent. But as you know that transition probability P21 prime is denoted in case of spontaneous emission. So here you see that this transition probability just depends on the Einstein coefficient of spontaneous emission. So again, there is no external source. U nu is 0, you can say, right? So the transition basically does not depends on the external source. It depends only on the Einstein coefficient, that is A21 right now. So this you can say 2, and Einstein, name of it is Einstein coefficient of spontaneous emission. So this is the transition probability and Einstein coefficient. Third case is about to the stimulated emission, and let us see here. In cases of stimulated emission, you know that atom is already in excited state, and one photon basically, or the energy of incident photon, you can say they interact. This is an electromagnetic interaction, and because of that it jumps into the ground state and emits of a photon of the same frequency as of the incident photon. So both the photons have same frequency, same energy and same direction. So what about the transition probability? Transition probability here is denoted by P21 double prime, and that is again directly proportional to the energy density of the radiation. So this U nu is energy density of radiation. P21 double prime. So if you will increase the density of incident radiation, it means obvious that large number of atoms will get induced, and as a result you will get the coherent light, right? So when we write it in a proper way, P21 double prime, so a constant that is B21 comes out, that is proportionality constant and known as Einstein coefficients of stimulated emission case, and U nu. This is the third equation. This is known as transition probability. This one is the energy density. And when we combine these two, transition probability for the case of emission, we observe this one. So P21 was for the spontaneous emission, and we have given this Einstein coefficient to that. And P21 double prime is B21, and this U nu. So the total transition probability in case of emission is this one, and for the case of absorption it was B12, and you have written B12 U. So this is in case of absorption. Now my point is, for that I have make this video, that is what about the transition probability and Einstein coefficient. The information, basically the Einstein coefficient include about the energy width of the energy level, or sometimes that is called the decay width. Right, what is it? A decay width, actually there are two energy levels which you have seen in the explanation. So delta E, my mean is to say the thickness of this energy level, this one, and that is denoted by gamma. So you know from the principle, uncertainty principle, delta E and delta T is equal to H cross approximately, right? So here delta E is basically thickness of the energy level. So how to find out that, and what are the parameters? As you know that the lifetime of the excited state are different, and for an excited state, one of the excited state is 10 raised power minus 8 seconds. So if you put the value 10 raised power minus 8 seconds, you can determine the value of the decay rate, right? So all these information of the decay rate and lifetime of the state are hidden into the Einstein coefficients. So because of that, the transition probability basically depends on the Einstein coefficient, and one can say that uh, the which actually emission dominate, spontaneous emission will dominate, or the stimulated emission will dominate on the basis of Einstein coefficients, right? Because these are related to the two different process, and they include the energy information, energy width, and lifetime of the state, etc. These informations are hidden into the Einstein coefficients, right? And with the help of these, one can explain that B21 dominate or A21 will dominate in the laser process. So in the next video we will see the relationship of Einstein coefficient, and on the basis of that we will determine that which process basically dominates for the laser action. If this video is helpful to you, then please like